Hello, everybody, and welcome back to another Teach Astronomy stream, the first in the new year. Welcome 2021. Hope everybody's doing all right today. As usual, since this is a Monday stream, we're going to be doing book stream. Very exciting. Again, first book stream in 2021. I might be fidgeting with my camera a little bit because my setup changed very slightly, but it's enough where I can't figure out where the center of the frame is. But that's okay. I think that's better. Welcome. I hope everybody had a great holiday season if you celebrate, or, a Happy New Year if that was what you were up to. Everybody was safe and healthy. COVID is still a risk, so I hope nobody was traveling too much. Oh, thank you for the subscription, Alexandra. Thank you so much. I think you've been subscribing for 2 months. Thank you so much. I really appreciate it. That means so much. And we got an emote from you, I think. It says that we got an emote. We got, is that an Among Us emote? Sure looks like it. That's very funny. Hey, Turbo Slayer. Hey, Parzival. How you doing? I'm doing all right. Happy New Year. Thank you. I'm happy you're back. It's good to be back. It was nice to have a little bit of a break, reset, especially after the year that the world has had. But it's nice to start fresh. But I'm really glad to be back and streaming and stuff. It's really fun to hang out with you guys. So, like I said, today's an Einstein's Monster stream. Oh, thank you. Actually, it's just my actual wall. This is like my room, but we painted. So we painted half the wall. It was very exciting. One of our projects over break. But yeah, so we're going to be reading chapter 7 today. And I also looked ahead because I was getting the pictures for the PowerPoint, which hopefully doesn't crash the stream this time. We'll see. Oh, hey, Lynn Jersey. Thank you for the kudos. But yeah, hopefully it won't crash the stream today. We'll have to see. I messed with some settings, but if it does, I'll be back. Don't worry. Alexandra, you said you don't know how the subscription works, but welcome. Well, it really helps out the channel. If the subscription is what you're talking about. So it means a lot, really. But yeah, so we're on chapter 7, and chapter 7's super long. I think I had said earlier when we were reading this at some point that I noticed all of the chapters in this book were 18 pages. This one's 40. So it's a bit much. So we're going to be doing half of the chapter today. And I think that'll be our regular hour 45. And we're just doing our regular thing, reading, chit-chatting, having a good time. It looks like a chocolate sandwich with vanilla layer. I could see that. Yeah, it's definitely browner on screen. It's more red in here, but it's like a dark maroon kind of thing. Hey, Adam Altogether, how you doing? That's a fun emote. Oh, the emoji, Alexandra. Okay, yeah. I don't know why you get it's something with if you get subscribers, they'll give you a random emote or something. I have no idea, but it's fun, and it's a little Among Us emote. Trying to find the right page to start on. Did I pass it already? Probably. But yeah, I hope everybody's doing well, and I guess we will get started. All right. So, chapter 7. Let me get my keyboard out of my way so I don't accidentally hit all the keys. All right. So, chapter 7. Seeing with Gravity Eyes. A revolution is brewing. We're on the verge of being able to see black holes in action. For 400 years, astronomers have learned about the universe solely by using light and other forms of electromagnetic radiation. They measure properties of the stuff of the universe by the ways it emits and interacts with radiation. Then, in 2015, gravitational waves were detected for the first time. Gravitational waves are ripples in spacetime that travel at the speed of light. They offer a unique window into the intense gravity of black holes, neutron stars, and supernovae, and will allow astronomers to test general relativity in new ways. They reach us from vast distances and can be used to probe the universe just after the Big Bang. Seeing with Gravity Eyes promises to transform our understanding of black holes. That's the little intro section. A new way of seeing the universe. There have been two major revolutions in the way we see the universe. The first began in 1610, when Galileo took a newly invented device called a telescope and aimed it at the night sky. His best telescope had lenses a half an inch across, and it gathered 100 times more light than the eye. Ever since Galileo's time, astronomers have worked to improve his simple spyglass. 100 years ago, they began using mirrors instead of lenses to gather the light, since lenses sag when they're large and they don't bring all colors to a focus at the same location. In the modern era, astronomers have built optical telescopes 10 meters in diameter, either using single monolithic mirrors or mosaics of smaller hexagonal segments. The gain in light-gathering power in 4 centuries since the time of Galileo is a factor of 1,000,000. Hey, Ace's Hammer, thank you for the cheer. Said you changed your work hours so you actually have time to show up to these. Well, that's very exciting. I'm glad you said you always work, so I feel bad. It doesn't seem like you got less hours, and some more free time. But thanks for being here. Thanks for joining us. Thanks for the cheer. I appreciate it. Meanwhile, an additional gain in depth came from improving the way light is detected. The eye is an inefficient chemical detector. To give us the illusion of continuous motion, it must transmit the information that falls on the retina on the brain 10 times a second. Oh, to the brain, 10 times a second. That means that it only gathers light, or integrates, for 1/10 of a second. Photography was invented in the mid-19th century, and soon afterward, astronomers were using it to take pictures of the night sky. Light is captured chemically in a process that's no more efficient than the eye, but long exposure times give much greater detail. A real leap forward came in the 1980s when digital imaging was perfected. Charge-coupled devices, or CCDs, now have 80 to 90% efficiency in converting incoming photons into electrons and then into an electrical signal that can easily be digitized. CCDs are near-perfect detectors. The gain in detection efficiency over the eye is a factor of 100,000. Combining these two factors means that the best telescopes see a remarkable factor of 100 billion times deeper than the eye. This is the difference between a northern hemisphere dweller seeing just one external galaxy, M31, and a large telescope seeing 100 billion. It's the difference between seeing stars a few hundred light years away and seeing light that has traveled for 13 billion years. CCDs have improved so much that the number of photons recorded with large telescopes in the past year exceeds the number of photons recorded by all the human eyes in history. Hey, Roten Gen 101. Traders used to spy for ships, bringing goods with telescopes before Galileo. Yeah. Yeah, I think that's what they were originally made as spyglass kind of things, and Galileo and I think probably a couple other people who have been lost to time, were the ones who kind of turned it up to the sky. But yeah, they used to look and see, what ships were coming in to try to tell, I think what merchant, what goods they had. So then they would jack up prices if only one ship was coming in with sugar or something. So they'd be like, oh, we gotta put sugar up really high today or something like that. Based on what they would see, which is crazy. Because, I guess everything, there's a lot of things in history that were made for business first and then adapted for other uses, right? And that's one of them. The second revolution in seeing the universe played out over the first half of the 20th century. Ever since our early ancestors stared at the sky from the African savanna, astronomy has used a small sliver of the electromagnetic spectrum. From the bluest blue to the reddest red is only a factor of 2 inches in wavelength or frequency. The largest telescopes simply drill deeper into the same narrow slice of the spectrum. Technologies were developed to pry open the electromagnetic spectrum for astronomy. Viewing the universe in visible light is as limited as seeing in black and white compared to seeing in vivid color. Perhaps a better analogy comes from music. Visible light is 2 adjacent keys on a piano, while the electromagnetic spectrum, from radio waves to gamma rays, is the full set of 88 keys. The first invisible waves to be used for astronomy were radio waves. At the end of the 19th century, Guglielmo Marconi showed that radio waves could be sent and detected over large distances. And, as we've seen, within 30 years, Karl Jansky used a simple antenna to detect radio waves from the center of our galaxy. In the 1920s, two astronomers at Mount Wilson Observatory used a device that converts a temperature difference into an electrical signal to detect infrared radiation from a number of bright stars. But infrared astronomy didn't take off until more sensitive detectors were perfected in the 1970s. Observations at invisibly short wavelengths were impossible until astronomers could avoid the radiation being absorbed by the Earth's atmosphere. The X-ray sun was detected by a sounding rocket in 1949, and the archetypal black hole Cygnus X1 was first spotted 15 years later. X-ray astronomy advanced rapidly, with a series of satellites in the 1970s. Cosmic gamma rays were predicted years before they were detected by satellites in the 1990s. Oh, hey, Game Doctor, how you doing? Doc is here. Doc's in the house. We've played Among Us with Doc before. That was super fun. Thanks for tuning in. These capabilities give astronomers tools to detect radiation with wavelengths as long as 10 meters and as short as a thousandth of the size of a proton. Frequencies from 10 to the 8 to 10 to the 27th hertz. The extension and wavelength grasp from a factor of 2 to a factor of 10 billion attests to the power of technology to transform our view of the universe. Only a few sources can be detected at all wavelengths across the electromagnetic spectrum. And they're all active galaxies powered by supermassive black holes. Everything we learn about the universe involves telescopes gathering radiation. It's very easy to forget that we rely on indirect information. The universe is full of matter, dust grains, gas clouds, moons, planets, stars, and galaxies. We don't see this matter directly. We infer its properties by the way it interacts with electromagnetic radiation. Chemical elements are diagnosed by the particular spectral lines they emit or absorb. Dust grains reveal themselves by absorbing light and emitting infrared radiation. Moons and planets are seen in the reflected light of nearby stars. Stars are seen by the radiation they leak out as a byproduct of nuclear fusion. Galaxies are mapped using Doppler shifts of spectral lines from their gas and stars. All of this is indirect, and it only relates to 5% of the universe that's normal matter. The 95% that's dark matter and dark energy is still invisible to us because it doesn't interact with radiation. The astronomical objects are the actors, but the stage for this cosmic drama is also unseen. Astronomers trace the expansion of the universe using galaxies as markers of invisible space-time. Roten Jen said, check the wiki. There was only one radio astronomer for a while. Yeah, I think Professor Impey may have mentioned that earlier, but yeah, radio astronomy took a while to take off for sure. But the thing is, before Marconi, Chandra Bose found the radio waves. Yeah, I mean, I'm sure there. So Parzival in the chat is saying that there was another person that was the father of radio astronomy and radio science, and it's like many fields where like several people are accredited to discovering it or like being the first radio astronomers and stuff, because, or like radio scientists, radio wave scientists, because of how it was discovered, like, you know, like who did it first, really, because, like, you know, it's the kind of thing where like everyone thinks that Galileo made the telescope, but he didn't, kind of thing. Yeah, Hertz also found it before Marconi. Yeah, so it's you know, there's always some confusion with who actually discovered it, because it's always like who was favored by the history books at the time, you know. All right, let's see. Where was I? Did I read about the black holes yet? I don't think so. The detection of black holes is also indirect. The closest we get is information from the high-energy radiation in the surrounding corona that reflects off the inner part of the accretion disk. Then the mass and spin of the black hole can be diagnosed through X-ray spectral lines. Wouldn't it be nice to see the stuff of the universe without the intermediary of electromagnetic radiation? Wouldn't it be great to directly perceive the warping of space-time? We could, if only we had gravity eyes. The best analogy for what that might be like for a person is telepathy. A brain is a lump of living tissue weighing about 3 pounds. In more detail, it's an electrochemical network consisting of billions of neurons and trillions of connectors between them. But this knowledge hasn't told us where we store memories, emotions, momentary thoughts, or our sense of self. Seeing the universe in terms of gravity would be as profound as seeing someone else's thoughts and feelings as they experience them. That's the end of that section. Oh, Parzival's asking about the vaccine. I don't think Doc's gotten it. I haven't gotten it. It's a very slow rollout here in the U.S. It's happening, but it's going to all of our healthcare workers first, of course, as it should. But it's probably going to be a while before the rest of us get it. I know some people. Yeah, Biden got it probably because he's gonna be the leader of the country in like a month, which is good, and he's older. But yeah, they're doing healthcare workers and people that are in like they call it extended stay facilities or something like that. So for like homes for the elderly and things like that, where there's like regular care for like older people. Yeah, there's always some political noise in the background here in the U.S., right? I'm waiting till January, you know. It's nice because you don't have to. I wouldn't say you don't have to worry about it anymore, but it's nice not hearing a bunch of crazy things from the news every day and like needing to check it all the time. I've been able to relax a little bit more. But anyway, I was going to show you guys a figure. So we're going to click the PowerPoint for the first time today. Let's hope it doesn't crash. Okay, I think we're good. So this is the figure that was in with the book, and about the gravity eyes stuff. So this is essentially just explaining the different abilities of sight abilities of things. So it says, there have only been 3 revolutions in our way of seeing the universe. For most of human history, we were limited to naked eye astronomy. In 1610, Galileo used the telescope as a way of gathering more light. And in the 4 centuries since, telescopes have reached over 10 meters in diameter. In the early part of the 20th century, a series of technological advances, involving new detectors and telescopes in space, opened up the electromagnetic spectrum for astronomy, from radio waves to gamma rays. In 2015, the detection of gravitational waves allows us to see the universe with gravity eyes for the first time. So essentially just saying if this is like a timeline sort of thing, it shows you like how much we could see for this long stretch of time. And then we hit 1600 AD where we get the telescope and it expands. And the electromagnetic spectrum expands. And then, it just continues to get larger. Hi, Charlie. How you doing? Welcome back. Happy New Year. Do we still know what gravity is? It's a force, right? An invisible force. And we can see in gravity eyes. All right, so the next section is ripples in spacetime. What are these ripples in spacetime? Recall that in general relativity, matter governs the curvature of spacetime. Gravitational waves happen at any time a mass changes its motion or its configuration. Waves of distorted space radiate out from the source in the way that waves move away from a stone thrown into a pond. In the theory, the waves travel at the speed of light, and they weaken with distance from the source. The space distortion is extremely subtle for most matter in motion. The strongest gravitational waves come from the most dramatic cosmic events. Black holes orbiting each other and colliding, neutron stars orbiting each other and colliding, supernova explosions, and the violent birth of the universe itself. Imagine perfectly flat space-time with a circular ring of particles lying in a plane. I think of it as the plane of my computer screen. The particles only serve the purpose of making invisible space-time visible. If a gravitational wave passes directly into or out of the screen, The ring of particles will follow the distortion in spacetime, alternately squashing slightly in a vertical and then a horizontal direction, repeating the distortion periodically. And we have a figure for that. So let's risk it and go back to PowerPoint. Every time I turn on the PowerPoint, I'm afraid this stream is going to die. But hopefully it won't. Okay, so this is the figure. So it says, gravitational waves are sinusoidal oscillations of spacetime, shown in the top panel as one complete cycle of amplitude variation. So here's the amplitude variation, I believe. Two independent polarizations of gravitational waves, shown in the lower two panels, here and here. I hope you guys can see my cursor. It'd be awkward if you couldn't. So those are displaced by 45 degrees rather than the 90 degrees of electromagnetic waves. The waves move perpendicular to the page in this example. The middle panel shows the arms of an interferometer, added to suggest how such waves might be detected. Distortion in these diagrams is highly exaggerated. In practice, deviations from circles would be imperceptible. So yeah, very cool. Where's my mouse? Okay. Every time it comes back from PowerPoint, I'm so thankful. Okay. Like other waves, gravitational waves are described by their amplitude, frequency, wavelength, and speed. The amplitude is the fraction by which the ring of particles distorts as the wave passes. The frequency is the number of times the ring of particles stretches or squeezes per second. The wavelength is the distance along the wave between getting tongue-tied. Jesus. The wavelength is the distance along the wave between points of maximum stretching or squeezing. These waves travel at light speed through the cosmos, flexing physical objects, but also passing through them as if they weren't there. In the analogy, we imagine a circle flattening and stretching into an ellipse. But that far overstates the actual distortion for a typical gravitational wave. The imaginary ring of particles deviates from a circle by 10 to the negative 21, or 1 part in 1,000 billion billion. To detect space-time shimmering by such a tiny amount sounds like an impossible experiment. Indeed, the person whose theory predicts gravitational waves at first did not believe they were real. We've seen that Einstein didn't believe that black holes existed, and he underplayed the importance of gravitational lensing. In 1916, following a suggestion by his colleague Henry Poincaré, he made an analogy with magnetism. When an electric charge is moved back and forth, the oscillating disturbance creates an electromagnetic wave, such as light. Einstein knew that matter curves space, so it seemed logical that matter in motion should create an oscillating disturbance of space. Einstein had terrible problems making this idea work. The analogy is flawed because electric charges can be positive and negative, while in gravity there is no such thing as negative mass. Einstein struggled mightily with coordinate systems and approximations to do the necessary calculations. He derived 3 types of wave, then was mortified when Arthur Eddington showed that 2 were mathematical artifacts that could travel at any speed. Eddington joked deadpan that they might even propagate at the speed of thought. By 1936, Einstein had made up his mind. Every time he tried to write a formula for plane waves, like our computer screen analogy, he encountered a singularity where the equations blew up and the quantities became infinite. He wrote a paper with Nathan Rosen, his student at Princeton, titled, "Are there any gravitational waves?" To which the answer in the paper was an emphatic no. He submitted it to the prestigious journal Physical Review and was stunned when an anonymous referee rejected it and pointed out several errors. Einstein had never been subjected to peer review before. In Germany, his papers had always been published automatically. He wrote a testy letter to the editor. Quote, "We, Mr. Rosen and I, had sent you our manuscript for publication and had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case erroneous, comments of your anonymous expert." End quote. But Einstein was wrong, and another young colleague pointed out his mistake. Ironically, a day before he was due to give a talk at Princeton titled "The Non-Existence of Gravitational Waves." After Einstein and Rosen published their corrected paper in another journal, physicists remained divided. Many thought that gravitational waves were a mathematical construct with no physical meaning. But after all his early misgivings, Einstein became convinced that they were real. The success of his theory gradually persuaded him to trust its predictions. That's the end of that section. Gotta take a little drink of water really quick. How's everybody doing today? Is everyone back to school, back to work? Hi, Single Coded. How you doing? Welcome back. Everybody, I hope everybody had a relaxing break, even if it was only... I know some people here are students and some people are just have regular jobs, and some people are retired, but I hope everybody enjoyed whatever break they got and got to see family if possible, or see friends if possible, even if just virtually. I know I had a little virtual party. I don't know if anyone else is interested in video games, specifically Animal Crossing, but I celebrated New Year with, I Skyped with my family for their New Year, because they're a few hours earlier, and then me and a friend met up on Animal Crossing and celebrated with our villagers. So it was very cute, very chill little New Year, you know. So I hope everyone else had a chill New Year. Have I ever used Universe Sandbox? I have for a little bit. I don't own it, but we had it. I think a friend of mine had it, and I've messed around on that before. I want to get it now because I have a nice, a better setup now. I've got a computer that can run a lot better than my, regular laptop. So I want to try that out. Some people have nothing better to do. Yeah. UK college smacks with their exam for 2 to 3 days. It was fun. Oh, did your college have exams right in the middle of the holidays? That's unfortunate. Yeah, here we it's the break of the end of the first semester is right before. It's the week before the holidays usually, or 2 weeks before, first or second week of December, and then schools here usually take a break and then start back up sometime in January. It depends on what system they use, because some places use quarter systems, some places use 2-semester systems, some places use trimesters, and I don't understand that at all. But yeah, I want to try Universe Sandbox. I think that'd be something fun to do sometime with Chris too, with Professor Impey, because I've never asked him if he's used any of the actual simulation software that theorists use and stuff, because obviously it's a little bit more complicated than Universe Sandbox, but Universe Sandbox is a good consumer grade kind of let's mess with the universe and mess with gravity and see what happens. But I'd love to see him mess around with that and see what he thought of it. I think that'd be fun. So definitely something to do in the future. And I'm excited too, because we're getting closer to the end of the book. Actually, a lot closer, because I didn't realize a good chunk of this is the bibliography. That's all notes at the end. That's a lot. Damn. And then at the end, when we're finished reading the book, we are going to do a stream with Chris where we get to ask him a bunch of questions about the book, about black holes specifically, about all that good stuff, author things. Yeah. Oh, Single Code is heading back to work. Yeah. It was a nice time off. I mean, my work has been strange because this is my work and I work from home work, but yeah. It's a nice little break. And I'm glad you all seem to enjoy it, although Parzival had to get through some tests. All right, well, I will continue. So, an eccentric millionaire and a solitary engineer. Space-time ripples seemed so difficult to detect that physicists ignored them. They were buried in the drawer of physics esoterica for 20 years after Einstein and Rosen's paper was published, until they caught the attention of an eccentric American millionaire named Roger W. Babson, If you never thought physics could make you rich, pay close attention to this story. Babson's interest in gravity started with a family tragedy. His older sister drowned while he was still an infant, and he later said it was because she couldn't fight gravity. In his career, he applied a version of Newton's laws to the stock market. What goes up must come down, he said, and also, to every action, there is a reaction. He foresaw the 1929 Wall Street crash, and he generally managed to buy cheap shares on their way up and sell them before they headed back down. Babson said he owed gravity a debt for helping to make him a millionaire. Babson started the Gravity Research Foundation in 1949 and sponsored a high-profile essay contest on ways to counteract or nullify gravity. Needless to say, the contest was won by some less than rigorous essays. The Foundation's promotional material talked about control of gravity. Sorry, there was some glass crashing outside from one of the neighbors. The Foundation's promotional material talked about control of gravity in the context of Jesus walking on water. Reputable physicists avoided it, and science popularizer Martin Gardner called the Foundation, quote, perhaps the most useless project of the 20th century. In an attempt to regain credibility with the physics community, Babson spun off an institute whose sole purpose was to fund pure research into gravity. He asked the Princeton physicist John Wheeler, who invented the term black hole, to persuade his colleague Bryce DeWitt to head the new institute. DeWitt organized a landmark conference on gravity and general relativity at the University of North Carolina in early 1957. The conference energized a young generation of gravity theorists. The discussion on gravitational waves centered on whether or not they carry energy. Richard Feynman's sticky bead argument convinced most of the audience. He asked them to imagine two separate rings of beads that fit snugly on a metal bar. When a gravity wave passes through the bar, its force causes the rings to slide back and forth slightly. Friction between the rings and the bar means the bar will heat up. Thus, energy is transmitted from the wave to the bar. A young engineer named Joseph Weber was in the audience, and he paid careful attention to this talk. Weber was born into a poor Lithuanian immigrant family. His name anglicized to ease assimilation. He dropped out of college to save his parents' money and joined the Navy, rising to the rank of lieutenant commander. During World War II, he headed electronic countermeasures work for the Navy. After the war, he joined the engineering faculty of the University of Maryland. Weber's scientific life was a series of near misses. George Gamow could have given him the PhD project of detecting microwaves from the Big Bang, but he didn't. And the Nobel Prize for the later accidental discovery was won by Arno Penzias and Robert Wilson. In 1951, Weber presented the first paper on the idea of masers and lasers, but it was Charles Townes who, after reading his paper, pioneered these technological innovations. But Weber's most painful miss was gravitational waves. Oh, when Jersey said, you thought we were going to have a test at the end. Oh my gosh. No tests here. Don't worry. This is just fun reading. Fun reading where you can learn something. Hi, Mad Lad Science. How you doing? Good morning. Good morning. Welcome to the stream. Inspired by the conference in Chapel Hill, Weber wondered how he might detect gravitational waves. He came up with the idea of a metal cylinder suspended on wires and placed in a vacuum chamber to isolate it from the environment. His cylinder was 1.5 meters long and 2/3 of a meter in diameter, and weighed 3 metric tons. Oh my god, wait, that's huge. Sorry. It was surrounded by piezoelectric sensors to convert mechanical vibrations into electrical signals. If a gravitational wave passed through the cylinder, Weber hoped, it would ring just like a bell hit with a hammer. And there's actually a picture of him with this massive 3-ton cylinder that I will show you now. There he is. So that is Joseph Weber and his pioneering gravitational wave detector, set up in a physics lab at the University of Maryland. An identical detector was set up 600 miles away. A real signal would register with both detectors. Like Grote Reber before him, Weber was for a time the only person doing experiments in this new field of astrophysics. He announced the detection of gravitational waves in 1969, But nobody could replicate his results, so his reputation suffered. So there he is. He actually reminds me of a character from a TV show I watch. I don't know if anyone, I know not all of you are from the US even, and even less of you might watch this show, but there's a show called Schitt's Creek, like SCHITTS. And it's a comedy show on Pop Network. I don't actually know like what the bigger company is that makes it, but there's a guy and his name is Dan Levy, and he plays one of the characters in it. It just reminds me of him a little bit. I guess he might look like Disney, like Walt Disney, maybe a little bit. All right. And after the figure, I will go back to... Weber set up one of his bars in a room at the University of Maryland, and an identical one 600 miles away at Argonne National Laboratory outside Chicago. Their data link was a high-speed phone line. The reason to have two identical detectors was to eliminate local noise caused by thunderstorms, mild earthquakes, cosmic ray showers, power glitches, and anything else that might jostle the cylinder. If a signal wasn't recorded simultaneously at both locations, it would be discarded as spurious. Apart from the local events, the constant noise in Weber's experiment was the thermal motion of atoms in the aluminum cylinder. This unavoidable agitation caused the cylinder to vary erratically in length by roughly 10 to the negative 16 meters, or less than the size of a proton. Weber thought he had hit the mother lode when he saw signals that were well above the level of this thermal noise. In 1969, he published the detection of gravitational waves and announced it as one of the major gravitational and relativity meetings. A year later, he claimed that many of the gravitational waves originated from the center of the Milky Way galaxy. Physicists were all surprised, and many were stunned. But most were delighted that a central prediction of general relativity had been confirmed. Weber was celebrated. His picture appeared on magazine covers. He was famous. Oh, you said it's a CBC TV sitcom? I think it might be CBC, Schitt's Creek. It's a good show. Anyway, that's a very much tangent. Okay, so he was famous. Then it all began to unravel. Weber's signal from the center of the Milky Way implied that 1,000 solar masses per year were being converted into gravitational wave energy. The young theorist Martin Rees calculated that such a loss of mass would cause the galaxy to become unglued and fly apart. Other experimenters tried to replicate Weber's results. Weber bars sprang up around the United States and in Germany, Italy, Russia, and Japan. Ron Drever, whom we'll meet later, set up several in Glasgow, a place not exactly short of bars. That's funny. There's even a Weber bar on the moon, left there in 1972 by Apollo astronauts. By the mid-70s, several groups had improved on Weber's original design and sensitivity, often cooling their detectors to reduce thermal noise. Nobody detected anything. Other physicists questioned Weber's experimental technique. He seemed to have miscalculated the statistics of coincident events in his widely separated detectors. Damningly, he claimed a peak in his data every 24 hours, when the center of the galaxy passed overhead. It was quickly pointed out that gravitational waves should pass through the Earth like a knife through butter, so he should have seen a peak every 12 hours. In 1974, at the 7th Major Gravitation and Relativity Conference, senior IBM physicist Richard Garwin denounced Weber and his data. Soon, the rest of the physics community agreed. Weber had been guilty of poor experimental technique and worse, bias in his presentation of data. Despite this, he never wavered in his belief that he had seen ripples in space-time. By the end of his career, he was a largely embittered and solitary figure. Yet, Weber's work spurred innovation, as other physicists were motivated to detect this signal prediction of general relativity. John Wheeler wrote, this is all in quotes, "Following our work together in Leiden, he embraced gravitational waves with religious fervor and has pursued them for the rest of his professional career. I sometimes ask myself whether I imbued in Weber too great an enthusiasm for such a monumentally difficult task. Whether, in the end, he is the first to detect gravitational waves or whether someone else, or some other group does it, hardly matters. In fact, he will deserve the credit for leading the way. No one else had the courage to look for gravitational waves until Weber showed it was within the realm of the possible." End quote. Despite the discouraging results of the Weber experiments, there was a glimmer of hope. In 1974, Joe Taylor and Russell Hulse were using the Arecibo 305-meter radio telescope for pulsar observations. Oh, that's so sad. Arecibo's dead now. Rip Arecibo. Anyway, they found a pulsar spinning 17 times a second, but noticed a systematic variation in the arrival of the pulses. The variations had a period of 8 hours, which suggested a binary system. Additional observations showed that PSR 1913 plus 16 was a pair of neutron stars in a tight orbit not much larger than the size of the Sun. Taylor and Hulse realized that general relativity predicted orbital decay in the binary system. The orbital period should decrease by 77 microseconds per year as energy is carried away by gravitational waves. Pulsars are exquisite clocks, so the tiny period shift was observable. And we have a figure for that. Let's check it out. There she is. So this says orbital decay of the binary pulsar system PSR 1913 plus 16 as observed at at Arecibo. The system loses energy by emitting gravitational wave radiation, and the data points perfectly fit the theoretical prediction of general relativity. These observations were a strong affirmation of the validity of general relativity and indirect confirmation that gravitational waves exist. So that is what they found. It's pretty cool. Ooh, what is this? Looks like Student McLeod found us. Well, that's cool. I've seen this GIF before. This one's a still, which is good as well. But yeah, it's cool. It's let me pull this up really quick. Chrome loves to not work with Streamlabs. There we go. Now you guys can see it. Yeah, like Student McLeod said, this is a binary system creating gravity waves. So normally, you could, if you pull up a GIF of this, these are spinning, and these waves continue to flow out as if like, the waves look like when you throw a pebble into water, and then they ripple out. But these two, you can see that they're starting from where the stars are. So yeah, very cool. Thank you for that. All right. The orbital decay detected precisely matched the prediction of general relativity. This was strong, although indirect, evidence for gravitational waves. Taylor and Hulse were awarded the Nobel Prize in Physics in 1993 for making this sublime observation. The binary pulsar pointed the way forward. Another dozen systems were discovered. Astronomers realized that binary black holes should exist as well, with stronger gravity and therefore more powerful gravitational waves. With a sufficiently sensitive detector, perhaps these waves could be detected directly. Oh gosh. Sorry about that. I totally just hit the mic, and if anyone was wearing headphones, I hope I didn't explode your ears. The mic is just in the most precarious place. It's like right on the edge of the desk. Oh, and that's the end of that section. So we're gonna pause a second. We have 14 viewers right now. That's so exciting. I'm so glad everybody was excited to come back. I was very worried that, I mean, I guess we're in the middle of a book, so like you gotta keep coming. But it's always scary to take a break from something that's very regular, and especially since our channel's so new, and you're never sure if everyone's gonna come back or not. But so, do they solve the GR equations numerically? How do you? What do you mean by numerically? No closed form solutions. I'm not sure. Oh, your questions? You can If you have, this is a question. If you guys have any questions where it's, more astrophysics kind of questions, because disclaimer, if you haven't been here before, I am the Twitch expert and the reading expert and the streaming part of our group. That's kind of my area of expertise. I did film and television for my major and hopefully career. But the rest of the team is more of the, especially Professor Impey is the astrophysics expert. So yeah, if you guys have questions like that, or questions about amateur astronomy that you'd want us to talk about on our Friday streams, you can email them to, actually, wait, let me check. I want to make sure it's either Astronomy SOTA or it's ASOTA. So let me just make sure I know which one that is. I think it's, hold on. I got this. Oh, it's Astro Curiani, welcome. No worries about being late. That's okay. Absolutely no worries. I am doing this the most roundabout way, and I am going to the Active Galactic Instagram and checking our old posts about live sessions. Oh no. It is not there. Oh no. Okay. I'm doing it in a more roundabout way. I'm going to message Matthew, and I will give you the answer by the end of the stream, hopefully, if he responds. Oh, I have it. I already asked Matthew. This is amazing. Okay. It is astronomy spelled out. SOTA at gmail.com. There you go. So, so if you guys have any questions that are not about the book, that you would want answered in Professor Impey's Q&A live streams, or in our news streams, or our amateur astronomy streams, then you can send them to that if you are not here, if they're longer questions, stuff like that. Let me just gonna check up on the chat. Oh, Parzival, you were eager to hear the book sessions. Yeah, I'm glad you guys are here and enjoying them. It means a lot. TST at 1906 to stat. We'll go with. I'm glad you're enjoying it. Yeah, we try to make it a fun, chill environment to learn some astronomy stuff, because especially with the sciences, astronomy less so. I feel like astronomy is the most approachable science, but it's tough to sometimes just jump in and be like, okay, I'm gonna read this very heavy textbook, or I'm gonna take this class, and sometimes it's just a little much. So we want to provide a way to build community while also learning a little bit. So yeah. As far as when is Matthew and Michael going to come back, I have to talk to them, because I know Michael's semester, well, both their semesters doesn't start until, because Matthew has a holiday break as well, even though he's not a student. He works at the U of A. And they don't come back until next week, I believe. So I'm not sure if they'll want to stream this week. I'll have to check. Hopefully they will. But that should be on the schedule by the end of today. If we're doing this week. If not, I'll probably say something in the Discord to let you know. But if you don't see anything on the schedule by late tonight, or tomorrow morning, then we probably won't be doing this week. I just want to make sure I came back, because I promised you guys that we would be back on Monday. Roentgen said there's very limited scenarios for analytic solutions to the general relativity equations. Okay. Honestly, you probably know more about general relativity equation stuff than I do. I know the I mean, I was going to say I know the general idea of general relativity, but not so much the mathematical side of it. I think that's all the questions that were asked. But yeah. Looks like we have just a couple more pages left, actually. I think we might be... How many pages are these chapters normally? Because I could have sworn that they're normally like 18 pages. And that this one was going to be super long. But it seems like it's not that long. But it also... I definitely can't read the whole thing. Because that's too long. Maybe these are longer than I thought. Sorry, guys. We're just gonna... Okay. Sorry for the pause. Just trying to figure out where to stop. We'll see. We'll see. We're reading Einstein's Monsters by Impey. I didn't know there was another one. Wait. Who's hold on, I'm gonna look that up. Oh. What? Oh my gosh. Oh, okay. That's intriguing. Okay, so there is a this is a question that I'm going to ask Professor Impey. But as T-Stat, I'm gonna call you, just informed me with their question. We're reading Einstein's Monsters by Professor Chris Impey. So it's a, nonfiction astronomy book. But there is another... I'm sorry if you guys can hear that. There always seems to be a leaf blower on Mondays. But there is another book called Einstein's Monsters that was published in the 80s. That is a collection of short stories by a British writer named Martin Amis. Amis? Amis. Martin Amis. But that would be... I mean, it's probably not allowed because of copyright things, but that would be really cool if we could read a short story from there or something on here when the book's done. Because I imagine... And this is when I said it's a question to ask Chris. I imagine he could have been inspired to name his book after one of those short stories or something that might have resonated. So I'll have to see. You wonder if he's Amish. Martin Amis is Amish. Martin Amis. That'd be funny. Right. Is Amish a thing in Britain? I guess so. Maybe. I don't know. Is that just an American thing? I don't know. If anybody's from the UK, tell me, do you guys have Amish people? Or is that just in like Pennsylvania Dutch country? That's a really random question. I don't know how we reached this point. This is a science stream, I promise. All right. So next section is when black holes collide. This is the story of how two black holes formed, and how in the blink of an eye, their collision unleashed a torrent of gravitational waves containing 10 times more power than the light of all the stars in the universe. It's also the story of the birth of a new field of astronomy. It's 11 billion years ago, and the universe is a cozy place, 3 times smaller and 30 times denser than it is now. This is the construction phase of the universe, when galaxies are small and dense, merging with one another and actively forming stars. In one small, unremarkable galaxy, 2 massive stars form close to each other in a chaotic region of gas and dust. They're 60 and 100 times the mass of the sun, as hefty as stars can get. Within a few million years, a cosmic snap of the fingers, both stars consume their nuclear fuel. The more massive star lives faster and dies first. But as it becomes old and bloated, its smaller companion steals gas from it, overtakes it in mass, and becomes a black hole first. The black hole sucks gas from its companion, cloaking the pair in a shroud of gas that's churned up by the orbital motion. The gas also sucks energy from the orbit, bringing the two stars as close as Mercury is to the sun. Then the second star dies and becomes a black hole. At the end of this phase of vampirism, two black holes remain. Each hides 30 times the sun's mass behind the impenetrable veil of an event horizon 150 miles in diameter. They orbit each other warily, locked in a gravitational embrace. For 10 billion years, nothing happens. The pair orbit in silence and in darkness, eking out a tiny dribble of gravitational waves that brings them imperceptibly closer. Beyond, the universe gets larger, older, and colder. The cosmic expansion rate transitions from deceleration to acceleration as the baton passes from dark matter to dark energy. Star formation peaks and declines, and, no doubt, on surfaces of numerous Earth-like planets, alien civilizations rise and fall as well. Meanwhile, on the planet we call home, 3 billion years after life started, it is still exclusively microbial. Then comes a crescendo of activity. As the black holes approach each other, the gravity gets stronger and more gravitational waves are emitted, shrinking the orbit and accelerating the process. The last phases take just 0.2 of a second. The black holes increase their orbital speed and enter a death spiral. Space-time is turning like a pot of water brought to a hard boil. Gravitational waves are created with a frequency that matches the orbital period. It rises quickly from 35 Hz to 350 Hz. To approximate this in sound, you'd have to whip your hand up a piano keyboard from the lowest A to middle C in a fraction of a second. Think of a familiar orbit, like the moons around the Earth. That takes a month at a separation of 250,000 miles. At the end of the death spiral, these two black holes, each 10 million times more massive than the Earth, are about 100 miles apart and hurtling around each other 300 times a second, or at half the speed of light. This isn't an orbit. It's insanity. I'm going to pause there for a second. There are no Amish communities in the UK. Weren't they from Germany? I don't know. Maybe they were from Germany. I think it's very possible. Something to do some research on, I guess. Where are the Amish people that now live in like Pennsylvania in the United States? Where are they from? Something to think about. Thank you for the Dropbox links. I will not question where you get them from, but yeah, if you guys want, Parzival has Dropbox links for this book and for the other Einstein's monsters we mentioned. I've opened them before. They're fine. So, and he has a friend, so we're not going to question where the books come from, where the PDFs come from. Anyway, so we're at insanity. Then the event horizons kiss, and the black holes merge. The equations for this can't be solved. Even supercomputers strain to calculate what happens. The last phase is called ring down, where the merged object oscillates like a huge glob of dark jello before settling down into a single black hole twice the mass and twice the size of the individual black holes that collided. And we have a figure. Let's find that figure. There it is. So, here is... Oh, it's on the next page. So it says the final stages in the merger of two black holes left behind after massive stars have evolved and died as supernovae. After a slow approach lasting millions of years, the black holes spiral toward each other, merge, and reverberate before settling down. This entire sequence takes less than 0.2 seconds. The middle panel shows the gravitational wave signal predicted by numerical relativity, and the lower panel shows that the two black holes merge at a speed more than half the speed of light. So, yeah, so this is just showing, this is what it would look like, per se. This, as they said, is the gravitational wave signal predicted for this crazy thing. And then this is the speed. So very cool. The Amish have it written. Wait. I'm just looking at stuff. Oh yeah, Quakers. I think Quakers are different. I believe. I think they're very similar. Quakers and Amish. But I think Quaker is the religion and Amish is the lifestyle, maybe? I'm not sure. Maybe Amish is a lifestyle and a religion. I'm not positive. But the Amish originate from Switzerland, from Adam altogether. That's interesting. Parzival tried to send something that was vulgar towards his college exams, and it did not go through. But he said they were not fun. I'm glad you got through them. All right. After they kiss, the black holes have kissed. All right. In the gravity math, 5% of the mass is converted into gravitational waves. 1 million Earth masses turns into the energy of space-time ripples and escapes the entombment in the black hole. By contrast, the sun in 1 second converts 1,000 trillionth of the mass of the Earth into radiant energy. A pulse of gravitational waves flees the scene at the speed of light, traveling in all directions like waves in a three-dimensional pond. The biggest explosion ever recorded in the universe occurs in silence and total darkness. The ripples sweep through the voids of intergalactic space, weakening as they move away from their source. They pass through millions of galaxies, perhaps without being noticed. Meanwhile, on Earth, life moves from the oceans onto the land. The dinosaurs emerge and are extinguished by a global catastrophe, and a branch of the primate line develops large brains. As the gravitational waves wash across our neighboring galaxies, the Magellanic Clouds, our ancestors, learn how to harness fire. As they enter the Milky Way, humans leave Africa for the first time. The waves pass near the bright star Beta Voltanus as Albert Einstein is publishing his new theory of gravity. They pass close to a neighboring dwarf star, 82 Eridani, as a huge scientific instrument begins construction at widely separated locations in the United States. The instrument is taken offline for 5 years for upgrades, and is getting ready to take science data for the first time as the waves sweep through the solar system and bear down on the Earth. Marco Drago sits bolt upright. The 32-year-old postdoc from Italy is nursing a cappuccino at his computer monitor in the Albert Einstein Institute in Germany, when he sees a small squiggle on the monitor. Software initially flags the event as a glitch, but after automated cross-checks, the flag is removed. Marco realizes the universe is speaking, so he composes an email with the subject line, "Very interesting event." He's at the helm of the most precise machine ever built. And the next section, oh, thank you for the follow. Is that I4T? Thank you so much. Welcome to the Teach Astronomy family. We're a family. Oh my gosh, I have 19 viewers on. I was going to stop, but I can't stop now. You guys are all here. Yeah, we're about halfway through the chapter. But I know if I do the whole chapter, we're going to go way over time. So how about I do one more section? How does that sound for all of you guys? One more section, then we'll save the rest of chapter 7 for next time. And we can chit-chat a little after I'm done with this section, too. Does that work for y'all? I hope so. I'm going to take a drink of some water. Do we stop here and chit-chat? Or do we read one more section? The next section, by the way, is like 5 pages long. It's kind of long. Sincoda says, sounds good. I'm getting a spam call. That's fun. I'm not going to answer that. I'm busy. Gotta love those spam calls. Do you guys also get 1 million of those? I get 1 million spam calls. And lately I've been getting a lot of, so I have a podcast separate from this. And I have a podcast email. And I've been getting so many emails from people who want my money. And I'm not going to give it to them. But it's just a bunch of spam emails. All right. I'm going to do this for you guys. We're going to do one more section, and then we can hang out. Oh yeah, and well, I can tell you now. These sessions, these book streams, we do every Monday at 10 a.m. Pacific Standard Time for me, which is when we started today. I started like 10 minutes late, but the same time we started today. That is every week. And we also do on Wednesdays and Fridays, we do 2 streams. Wednesdays is our news stream or our like fun stream. We switch off every week because sometimes there just isn't enough news, so we do either like a focused topic thing or we do something fun and random. So those are fun, and I do that with my co-host Michael. And then on Fridays we do amateur astronomy stream with Matthew, and sometimes we'll look through a telescope. Sometimes we will talk about amateur astronomy equipment and how to get started. We had a guest on last time who was great. Also, if you miss any of these, we archive all the book streams, and we archive the special ones of the other 2 streams on our YouTube channel, which I can link as well. I'm going to do that really quick, because you can watch some of them on here for the first 14 days after we stream, but then after that they disappear forever. But we've found a way around that by using YouTube. It just takes a minute to it takes a day to refresh, or I'm so distracted right now because I'm trying to get you guys a link. That's not what I meant to say. Oh, I'm logged out. Oh no, hold on, wait. What channel is this on? It's on TeachAstronomy. The same as this channel. I know what's going on. It's okay. All right. Trying to do like 7 things at once. I've got like 10 tabs open. Okay, so that is where we archive everything that we archive from this channel. So if you ever miss a book stream, you can check it out there, or here if it's been less than 2 weeks, it'll still be here. We also have on there a really, really great stream that we did with astrophotographer Martin Ratcliffe. He was amazing. If you have any interest in amateur astronomy, that's definitely a great watch. But yeah, Wednesdays and Fridays. Fridays are typically 9 a.m. Pacific time. Right? Yeah, I believe 8 or 9 a.m. Pacific time. Wednesdays I actually have to check because Michael, my co-host for that one, his schedule has changed because it's a new semester for him. He's still an undergrad. So I have to see when we do that, but it's usually we either do like 9 or 10 a.m. like this, or we do sometime in the afternoon. We might keep doing sometime in the afternoon because I know for some people that doesn't work, but other people mornings don't work, so we figured trying to spread it out a little bit might be helpful. So yeah, definitely Mondays and Fridays we do 9 or 10 a.m. I mean 10 every time for Monday, but 9 or 10 for Friday. Wednesday we will figure out. But like I said, it'll be on the schedule by like tomorrow morning if we're doing it this week. Yeah. Yes. And they're all Pacific Standard Time because that's the easiest for me because that's what's in my brain. Yeah, whatever time I started this is this, whatever time that was for you, so about an hour and 20 minutes ago, that's when I stream every Monday. And then it's the same time or an hour earlier on Fridays with amateur astronomy. I hope that's not too confusing. Everyone was also saying that you guys get calls for people that want money. You Carolina boys, I had 3 hours. Yep. Yeah, my family's actually in New Jersey, so I'm very used to doing the constant conversion. I know we've got some people from India, though, some people from the UK, some people from Europe in general. I mean, I guess the UK is part of Europe, but you know. I don't think anywhere else. Do we have any Australians? Anyone in Africa? South America? Canada! Nice. Wait, Parzival, I thought you were in India. Did you move to Canada? Oh, you're from Spain. That's right. Single-coded. That's awesome. Oh, you're India. Why did you say Canada then? You're very confusing. All right. I'm going to start the next section. So, the most precise machine ever built. Oh, Charlie's Canadian, you said. Okay. Anyway, the most precise machine ever built. How many physicists does it take to measure a shift of a 10,000th of the width of a proton? Answer: over 1,000. Marco Drago is one of a small army of scientists working at dozens of universities and research institutions around the world on the most sensitive scientific instrument ever conceived. The story of how the Laser Interferometer Gravitational Wave Observatory, or LIGO, got built is almost as unlikely as the detection of ripples in space-time. When we left the story of gravitational wave detection, the field was in disarray. Nobody could reproduce Weber's results, and his scientific reputation was in tatters. Unfair as it might seem, the taint was widespread. Gravitational wave hunters were charlatans or fools, maybe both. But one group of researchers was motivated by their inability to reproduce Weber's results. It was a challenge to them as experimentalists to do better. They were buoyed by the pulsar spin-down observations of Taylor and Hulse, which was evidence that gravitational waves existed. One of these men, for it was and is a male-dominated field, was MIT physicist Rainer Weiss. As a child, Weiss fled Nazi rule in Germany with his family. He grew up in New York in a situation of benign neglect and threw himself into his passions of classical music and electronics. He abandoned his classes at MIT and had to start from the bottom as a technician in a physics lab. He returned to MIT but struggled to get tenure. And he grew frustrated trying to explain Weber's results to his students. I couldn't for the life of me understand what Weber was up to, he said. I didn't think it was right, so I decided to go at it myself. Weiss worked for a whole summer in isolation in a basement on an idea that grew out of discussions with his MIT students. Isolation. We're all familiar with that. And he came up with a detector that was an interferometer instead of a single bar. Imagine two metal bars at right angles, forming an L shape. If a gravitational wave arrives from above, the way it squeezes and stretches space means it makes one bar very slightly shorter, and the other bar very slightly longer. An instant later, the opposite happens, and the pattern repeats as long as the wave is active. Instead of trying to detect a single bar ringing like a bell, Weiss would have to detect two bars alternately flexing. Weber's experiment had been thousands of times too insensitive to detect its quarry. Weiss knew he had to make dramatic improvements. His clever idea was to use light as a ruler. His bars would be long metal tubes with the air sucked out, since light travels at constant speed in a vacuum. A laser at the crook of the L sends light of one wavelength through a beam splitter, so half goes down one arm, and the other half goes at right angles down the other. The light bounces off a mirror at the end of each arm, comes back to the crook of the L, and recombines at a detector. Normally, light waves return down each arm in perfect synchrony, peaks and troughs in lockstep. But when a gravitational wave passes through the instrument, one beam travels a slightly shorter distance than the other, so the peaks and troughs don't line up and the light intensity is reduced. And I have a figure. That's why I paused. I didn't say that. There's a figure. Let me show you. Here we go. This is a schematic design of LIGO. So the gravitational wave is depicted as arriving from directly overhead. So that's the lines up top here. Light passes through a beam splitter at along arms 4 kilometers long. Here's the beam splitter. Returning to be recombined at the photodetector, which is here. Oh, sorry. Had to yawn there. The test masses along each arm register the arrival of a gravitational wave as a very slight change in the length of the arms, which is recorded as an interference pattern by the photodetector. So, light comes in here, and essentially the test of if something passed through is if these arms, this light storage arm here and this light storage arm here, get very, very slightly longer or shorter, like so slight, that, you know, this, as they've said, this instrument has to be one of the most, if not the most sensitive instrument like in the world. Parzival said, asked if anyone's an MF Doom fan here. I personally haven't listened to MF Doom, but you said they died recently. That's very sad. I'm sorry to hear that. It's sad when somebody you admire passes away, you know. All right. Back to, where did they say the figure was? Okay, here we go. It sounds simple enough. The challenge is the exquisite precision of the measurement. Not only is the amplitude of a space-time ripple very small, its wavelength is very long. The typical frequency of the gravitational waves from a black hole collision is 100 Hz, which means that 100 ripples pass by every second. But the typical wavelength is 3,000 kilometers. The optimum length of the arms of such a device is a quarter of a wavelength, since shift by a quarter wave in either direction is the difference between enhancing the signal and canceling it. Weiss knew he couldn't make a 750-kilometer vacuum tube, so he imagined bouncing the light back and forth many times in a shorter tube. Weiss wrote up his concept in an MIT technical report in 1972. It may be the most influential paper never to be published in a scientific journal. The early road was hard. Weiss started work on a prototype interferometer with 5-foot-long arms. Even though it was hundreds of times smaller and less expensive than any viable tool to detect gravitational waves, he still had trouble scraping up enough funds. Administrators were dubious, and one particularly influential colleague, Philip Morrison, was deeply skeptical. In the early 1970s, there wasn't even strong evidence that Cygnus X1 was a black hole. Morrison thought black holes didn't exist, and since they were the strongest potential sources of gravitational waves, he thought Weiss was wasting his time. Weiss got some money from military sources, but that funding was cut off by an amendment to the Military Authorization Act, which barred the military from supporting civilian projects. One summer day in 1975, Rainer Weiss went to the Dulles Airport in Washington, D.C. to pick up famed Caltech theoretical physicist Kip Thorne, the man who won the bet with Stephen Hawking that black holes existed. Science works best when theory and observation work in concert. Theoretical predictions drive better observations, and observations drive deeper physical understanding. The genesis of the Ligo project occurred that steamy afternoon in Washington, when the experimentalist Weiss encountered one of the greatest theorists of our time in Thorne. Weiss had invited Thorne to a meeting at NASA headquarters on doing cosmology and relativity research in space. Quote, I picked Kip up at the airport on a hot summer night when Washington was filled with tourists. He didn't have a hotel reservation, so we shared a room for the night, recalled Weiss. We made a huge map on a piece of paper of all the different areas in gravity. Where was there a future? Or what was the future, or the thing to do? End quote. They were so consumed by their conversation that neither of them slept. Thorne hadn't read Weiss's technical paper on the interferometer concept. Quote, if I had, he said later, I had certainly not understood it. In fact, his magisterial book, Gravitation, includes a student exercise designed to show the impracticality of detecting gravitational waves with lasers. Quote, I turned around on that pretty quickly, admitted Thorne. He returned to Caltech, fired up to build an interferometer. But first he needed to recruit an experimental physicist. Weiss suggested Ron Draver of the University of Glasgow. Draver had done fundamental experiments on the smoothness of space and the mass of neutrinos. He'd built and operated a Weber bar, and he constructed an interferometer with 10-meter arms, 6 times bigger than the modest instrument built by Weiss at MIT. Thorne got Draver a half-time faculty position at Caltech. And by 1983, he'd built an interferometer with 40-meter arms there, using ingenious methods to increase the laser power and improve the isolation from seismic noise. Money started to flow, and the competition started to heat up. Weiss received a small grant from the National Science Foundation in 1975 to start his interferometer work. In 1979, the Caltech group led by Thorne and Drever got a significant grant, while the MIT group led by Weiss got a smaller amount of money. Caltech and MIT are intense science rivals. The Caltech group, with their 40-meter interferometer, were clearly in the lead. Weiss must have regretted recommending Drever to Thorne. Both groups were dreaming of a full-scale, kilometer-sized interferometer, but it was Weiss who seized momentum to visit the National Science Foundation. He pitched the concept of an interferometer on 2 sites with a price tag of $100 million. The design study that resulted was called the Blue Book, and it's the de facto Bible for detecting ripples in spacetime. Weiss and Driver were both intensely competitive. Thorne found himself in the role of intermediary and peacemaker. As the NSF made it clear that the two groups would not be funded separately, they found themselves in a shotgun marriage. Progress came in fits and starts. Continual delays over technical issues led the NSF to cancel funding. By the mid-1990s, Ligo was back on track, now led by Caltech high-energy physicist Barry Barish. Science is littered with projects where accomplished scientists failed because they lacked interpersonal and management skills, but Barish proved to be an adept manager. I'm going to just take a break really quick, take a drink of water. Before we wrap up this section today, I wanted to pose a question. So we still have several chapters left in the book, but if you guys, I think 2 chapters actually. So not too much, honestly. A couple more streams. But as I start getting ready to do the book stream with Chris, about, as like an Ask the Author thing, and also as we're preparing to get the next book because shipping takes so long and Matthew's going to have to send me the next book, what would you guys like to hear next? Because I like doing this and I want to continue doing this. My schedule could change after we finish this book. There's a chance. I am looking for like a full-time job because this is just like my side gig now. But I still want to keep doing this because this is very fun. So if you guys have another book by Professor Impey that you'd really like to hear me read, let me know. I guess I could also go take a full 180 turn and start reading The Great Gatsby because that is now in public domain. That was mainly a joke. But if you ever wanted to hear me read The Great Gatsby, let me know. And maybe I'll make my own Twitch channel and do that because that would be really fun. I love The Great Gatsby. An astrophysics book by the professor. Yeah, just anything by him. That's totally fair. There's a whole list on his website if you just type in Chris Impey on the computer. But I was just wondering if you guys had any that you particularly wanted to read because I'm gonna ask you guys first because you guys are the ones that are always here. So he most of his stuff is astrophysics, astrobiology, all nonfiction. But there's one that is a science fiction. Can you do a poll? Yeah, we can totally do a poll. I guess we could do a little poll in here. You know what? We'll wait on a poll, but I will make a poll. But maybe for the stream where we finish the book, we could do a little poll or something. Because I imagine most people who regularly come will be there. Yeah, that'd be fun. All right. Let's keep going. From the start, they had planned on 2 identical interferometers with 4-kilometer arms located on opposite sides of the U.S. in geologically quiet sites. One was near a mothballed nuclear reactor in Scrub Desert outside Hanford, Washington, and the other was in swampland outside Baton Rouge, Louisiana. The first stage, called Initial Ligo, or iLigo, had a goal of technology development. Actual detection was very unlikely. The second stage, Advanced LIGO, or A-LIGO, aimed to be sensitive enough to detect the gravitational waves that theory predicted. Barish wanted a facility and an infrastructure where all the major components, vacuum systems, optics, detectors, and suspension systems could be continuously improved. And I'm just now realizing I didn't copy any more of the figures over because I thought we wouldn't be reading anymore. So I'm just going to show it to you the old way, which probably won't work very well. But here's our figure. Gosh, it looks so bad. I'm so sorry, guys. Ugh. Well, essentially, I'll explain it to you. So it's essentially a chart that's or a graph that's comparing frequency to strain, which is the sensitivity of LIGO. It's a fun graph. And I'm realizing now it's very hard to explain. So apologies for my unpreparedness today. It won't happen again. But we're going to keep going. Okay. The far greater sensitivity of advanced LIGO required upgrades to almost every aspect of the experiment. The laser became more powerful to reduce the principal source of high-frequency noise. The test masses at either end of each arm were made heavier. Each test mass was a 40-kilogram cylinder of silica with a mirror attached, designed to detect tiny changes in the length of the arm. A 4-stage pendulum was used for suspension, and the isolation and noise cancellation was improved by an order of magnitude. LIGO has the largest and best vacuum system ever built, requiring 30 miles of welds with no leaks. The pipes are so long that they're a meter off the ground at each end as the earth curves under them. The most precise concrete pouring and leveling ever achieved was needed to counteract this curvature and keep the pipes flat and level. The vacuum is a trillionth of the density of air at sea level. The detectors are so sensitive, they can feel when a truck applies its brakes 3 miles away and hear lightning storms at a distance of 50 miles. Even more impressive, they can see the motion of individual atoms in their mirrors. The experiment is a technical tour de force. Initial LIGO ran from 2002 to 2010, and, as expected, it didn't detect gravitational waves. The upgrade to advanced LIGO took 5 years, and the work of 500 people. Advanced LIGO worked in an engineering mode for 6 months and hit pay dirt 4 days before it was due to start taking science data. Which brings us back to Marco Drago and the morning of September 14th, 2015. The soft-spoken postdoc plays classical piano and has written 2 fantasy novels in his time away from physics. Maybe we'll read those. When he saw the squiggle on his screen, he was immediately suspicious. It had the classic pattern of a black hole merger, a brief crescendo that researchers called a chirp, like the bird song of the universe. After over 1 billion years of travel across space, the wave passed through the Earth at the speed of light, jostling the detector at Livingston, Washington several milliseconds before it jostled the detector across the country at Hanford in Louisiana. Drago was skeptical because the signal looked too strong, too perfect. No one was expecting something so huge, so I was assuming that it was an injection. LIGO overseers kept the team on its toes by injecting false signals into the data stream. They're called blind injections. In 2010, a blind injection led to great excitement in a paper being written, and it was only when the paper was about to be submitted that the team was told the signals were fake. That's rough. Drago took pains to be sure. He called all the other sites and talked to a group leader to make sure nobody had injected a signal into the system. He even worried that someone might have hacked the system as a prank. After a dozen automatic and manual checks, there was no doubt that the universe was responsible for the signal. It stood out against the noise like a burst of laughter in a room full of chattering people. Gravity had spoken. That's a good line. Chris has so many good lines in here. There's also another figure, but I'm going to try to look it up before we stop streaming today, because it is the actual wave detection stuff, and I imagine I'll be able to find that somewhere. Let's find it. So I guess that's pretty much all of our stream today. I'm going to find this for you guys, and then we're going to be basically done. Ligo first detection. Let's see. Yes, here it is. Let's open that image in a new tab. Okay. So here it is. So here is the, so up, like in this part. Oh wait, you can't see where I'm gesturing, I don't think. Oops. There we go. Here we go. Hopefully you can see my cursor. But in the part where it's not like a computer drawn line sort of thing, these are the actual observations. So this is Livingston, and this is Hanford. And you can see it's just like very nothing noise, and then just huge spikes. And then this is the actual frequency in hertz down here. That's a little more clear to read than the actual signal. But yeah, it's very exciting, very cool. I have looked at that image several times. What are you Dropboxing over here? Parzival. Let's see. Oh, Astro Curiani suggested that we oh no, you're good. It's okay. Astro Curiani suggested that we read how it began. That's a good one. As long as we don't read how it ended before how it began, that would be. I'll let you guys pick, but I'm not doing it out of order like that. But yeah, that's a really good one. If Impey doesn't win, what about something by Sagan? I would love to read other stuff. I just need to clear copyright stuff. So the thing is, like, the reason we're mainly reading Chris's books is because Chris is part of the channel. I work for him, and and he's written many books, and they're very good. But also because since I work with him and he can like directly give me permission to do this, we'll never have a problem with copyright, or at least we shouldn't. The issue comes if like I don't personally know the author. Some like smaller authors though, for sure. Like, I mean, Chris knows a lot of people. I don't think he knows Carl Sagan or the Sagan estate, or whoever owns that now, like the copyright and stuff. But if we ever run out of Chris books, which will take a while for sure, or if we want to switch it up, you know, if we've done a few of Chris's books and we want to do something else, there's always the possibility that I could find someone that Chris would know that could get me in contact to see if we could strike a deal like that. That would be cool. You shook Sagan's right hand. That's awesome. That's so cool. That counts. That's very cool. Roten Jen suggested we read Anna Karenina. That is a long one. Is that in the public domain? I wonder. It probably is. That one's really old, right? I think it's really old. Yeah. But T-Stat suggested Humble Before the Void. I actually have that one here, and it's a very interesting one. So that's the one that's probably the most well, a lot of his books are just like straight like this one, like Einstein's Monsters, focused in on a certain topic about astronomy or astrophysics and lots of science. But that one, I've only read a little bit of it, but it's like the subtitle suggests, a Western astronomer, his journey east, and a remarkable encounter between Western science and Tibetan Buddhism. So Chris went to this conference with the Dalai Lama, like the real one, and his monks, and in Tibet, and got to do this whole conference and stuff and present astronomy. Like, he was kind of like, I don't know if he was the only like astronomer that was there or like one of a group, but he got to do a whole presentation for the Dalai Lama. The Dalai Lama wrote a preface to his book. It's crazy. But that's a really interesting one because it's very much, I think that one's more a memoir style kind of, or like it's more about his experience. So, you know, he You can see it sometimes in Einstein's Monsters. He gets into telling the story of like how history happened and stuff. And he has a really good voice for it. So I think that book is more that direction rather than like explaining a lot of the astrophysics stuff. So I think that would be a really interesting one too. But yeah, you have a series in Active Galactic and his personal YouTube. Yeah. So I will be, we'll definitely do a poll. Probably not next week, but like maybe the week after, whatever week is like the last chapter week. I'll set up a poll somehow. I'm pretty sure you can like integrate that into Twitch, and we will do that, and we will have a good time. What is this YouTube link? Let's see. Oh yeah, this is the so if you guys were interested, this is the symposium, that the link that there's a couple links that Parsifal's dropping right now. That is the symposium that Chris was part of, that book is about. So it's really interesting. But yeah, I think that about wraps it up for today. Thank you guys all for joining me. As I said, this means a lot because I was so worried that people were not going to come back after the holiday break, but you guys are all here and it was great. I hope you had some fun. And like I said, I will update that schedule to see. Really, the only question is I don't know if we're streaming this week because I know some people have conferences and stuff. They're virtual, but Matthew might be busy and Michael might be traveling home. So, because he was with family and now he's going back to school. But I will let you guys know. So thank you all for having, for joining and for having a good time, hopefully. And I will see you guys, if not later this week, I will see you next Monday. Bye.